Everyone, thanks for coming. My name's John Avina, and I have Bill Koran here. He has, as you can see on this slide, he is retired. He used to work with, is it SBW Consulting? Is that right?
Yes.
He was at SBW Consulting, and I'm going to totally butcher his bio, but I'm going to tell you what I think are the highlights. So there's a couple things. One is he was the one, I think, who was the major or a major contributor to the BPA M&V guides, which I think are great. And I've mentioned them in a few of these webinars. They are great, and you really should get them. They're online. And he was big in writing those. Also, Bill wrote ECAM, and he's going to show you some of what ECAM can do, but he wrote it. It's an Excel Excel tool, and he wrote it in VBA. He's I hope don't be insulted here, but he's a hack like I am. I wrote Report Maker for metrics. He wrote ECAM, and ECAM's pretty damn cool. It can do a lot of really neat things, and I was really impressed with it. Anyway, that's my bio. Bill will fill in. In fact, I'm going to stop talking, and Bill, why don't you take it from here?
Okay, John, thank you. Here's a brief look at my face for people who have, whoops, it went back off already. I'm just going to not be looking at my laptop, so I'm going to be looking at another screen. So those of you that haven't met me, hello, nice to have you here. I want to add on to what John said about the development of ECAM. I'd helped by a couple colleagues at SBW and elsewhere. The vast majority of the code is stuff I put together, and the implementation of it, the start of it was by me with I was actually looking for the name of somebody else, but there was a fellow named Doug Finn Bell who I worked with years ago at Honeywell. That one of the key things in ECAM was kind of the kernel of idea came from him. So there's been other things, and what I think I was good at in my career was taking other people's good ideas and implementing them. Not a great deal of creativity, but a lot of application. And I think that's what I tried to do with ECAM, is things that people were already doing, day typing for they're looking at energy use, things like that, and automate it and make it easier for people to do things that they do on a regular basis. So I have a few slides in here. Beyond that, I won't talk about myself, but John mentioned some references and another picture of the handsome guys. Yeah. So some references of my work. One thing that probably people haven't seen, the top one there, I actually modeled my house. I had major trouble with my HVAC at a new house where, construction quality, it's bad in a lot of places, and in new homes that are rushed, there's some crazy things that they do. And I have a fairly large house with a single zone HVAC, and they tried to make it serve 2 zones, and the equipment didn't even run within specifications because of insufficient duct sizing, et cetera. I managed to get them to redo the whole thing and put in a new high-end, high-SEER variable speed fan and compressor in my HVAC, and the efficiency evaluation organization site actually has an article I wrote about that, and I'll go into that, just a brief mention of that a little bit farther. So that's kind of interesting. You can do this stuff for use ECAM and modeling and regression approaches for anything from groups of buildings down to an individual residence or down to an individual HVAC unit. John mentioned BPA M&V protocols. I was primary author for the original protocols. I didn't list all of them here, but there's also a newer one there that I think is applicable for talking about analytics or diagnostics, and it's the potential analytics for non-routine adjustments. I've got another mention of that in a little bit here. A couple other things regarding uncertainty, which I think was really good work and respected. I had some PhD knowledgeable statisticians and economists sign on to some of that work, but it was my work. If you're interested in going into the depths and uncertainty, that's kind of a pretty deep dive and beyond what most of us need to do most of the time. Also, this is a pretty cool book, came out in 2015. I'm proud to say there was a couple ECAM, one chapter on ECAM, and ECAM was part of another chapter, but there's a lot more, far more stuff in there than ECAM's a very minor piece of it, but it's a useful reference. I wrote, after I developed ECAM version 7, after retiring, I did that in the winter of 2020 and 2021, I did an article on LinkedIn, introduces ECAM and also talks about the changes in version 7, and ECAM's sort of hosted my old employer, SBW Consulting. To my chagrin, they labeled version 7 as a beta version. In reality, I believe ECAM version 7 was more heavily tested than any prior version. So I've made a couple changes since the postings there. Being retired, I'm not tracking all that stuff. Wasn't very good about it before I was retired. But last thing, one more recent reference. This was part of this was based on some of my work, but it's a good reference from the efficiency evaluation organization put together by Leah Webster. And Leah Webster is one of the super nice people in our industry and a very much more well-rounded engineer than I ever was, having done a lot more hands-on work as well as worked on the details of M&V. So that's one more reference I wanted to mention. So let's dive into this a little bit. This is starting right off. Some of this is a review. I did a similar webinar for John 2.5 years ago, I think, for Abraxas. And before I did that, I wanted to thank John and Abraxas for having me again. Kind of, like I said, I'm somewhat out of the loop now, but that doesn't mean the knowledge I have is expired. And I really admire John in particular for being the most open-minded, most challenging, most direct engineers I know that is willing to, most of us, I have a little bit of a thin skin sometimes. John is somebody that I would guess probably has a pretty thick skin. He looks to be challenged. He looks to be argued with from the standpoint of wanting to learn, always learning. What a great thing and what a great company to work for, is a place where you have a leader that wants to learn, is not afraid to be challenged. I'll tell one little anecdote. Not a joke, but I find it rather interesting and reflective of the type of person there. John, on a couple of occasions, has asked me to review papers he was preparing. And the word he used in asking me to critique what he has done was savage it. That tells you the type of person that this is, a constant learner. He wants somebody to criticize his so that his knowledge gets stronger and he can make his case stronger. And to have his respect and be asked to do this is really an honor to be here because of the type of person he is. So thank you, John. Thank you, Abraxas. So now I'll dive in. What can be done with interval meter data? Here's just a small sample. Some of the things are fairly obvious, like schedule adherence. I'll give an example of that. What is the load during an unoccupied period? How well are things turned down? We've done a lot of work in this industry on commissioning and trying to make efficient perform better and stuff. And I know at the time I retired, people still didn't turn stuff off very well. And I suspect that hasn't changed. And I see no evidence that it's changed when I go about my day-to-day life and going into businesses or driving by places that are closed and things. You can actually detect economizer operation or lack thereof, or what the changeover temperatures might be. You can examine the use of night setup or setback of your thermostat temperatures. What is your peak cooling load? If you have to resize equipment or if you're getting new equipment, what is the real load in the building rather than just putting in the equipment that was there previously? You can actually detect what the peak is, extrapolate out from a good regression to what the maximum load might be under the hottest weather conditions. You can see whether there's electrical heating or not in a building that should be primarily perhaps heated with gas. I know that's changing with time here, but you might have excess electrical heating where reheat comes on prematurely or things like that. And of course, we can also use this data to compare with benchmarks. There's two types of variables. There's continuous variables, things we measure, power, pressure, temperature, and then we can segment data different ways. building type, equipment type. We're familiar with using bin weather data, and particularly in modeling or just examining data with interval data, we'll want to group data into different times. It might be by day types, it might be hour of day or occupancy period, et cetera. Different groups of time to group the weather for modeling or data evaluation. So because we have these two types of data, roughly, there's different types of data-driven models. We're all familiar in this group probably with ordinary regression, particularly if you're using typical heating degree day or cooling degree day models. And so we can have ordinary linear regression or change point linear regression, which I'll not really talk about it, but I'll show. In multiple regression, where you have multiple independent variables. You can have bin models where you can just lump your data into bins and group them and compare data at similar temperatures. Or you can have similar temperatures and similar time periods, a multi-dimensional bin model. And you can combine these into a hybrid. And so most models that use interval data are a hybrid bin and regression. You'll have different time categories and you'll perform a temperature regression for each of these different time categories. And figuring how to group those time categories or different categories together is a key challenge in trying to create these types of models. And of course, as the world, well, I don't really like to use the word smarter because I'm not sure we're getting smarter, but as there's more capability for analysis and artificial intelligence and things like that, that the models get smarter and smarter, and in some ways they get more and more abstract, it seems like, and hard to understand. I've tried to make the ECAM modeling fairly easy to understand so that you can use it for the diagnostics we're talking about today. So here's first example of a problem I saw. This was a hotel many years ago. And you see there's two clouds of data. Anytime there's two clouds of data, you want to think about segmenting your data. In this case, it's one chiller operation and two chiller operation. The obvious scenario here is the one chiller operation is the lower set of points. And you can tell on the upper set of points what a wide range of building loads. They're still running two chillers when one chiller could satisfy the load. And on the y-axis is shown the chiller electrical demand. And you can see how much higher the demand is running two chillers to satisfy the load. So clearly a waste of energy there, and when they should be running just a single chiller a lot more than they were. One other point I want to make about creating regression models when you're looking at data like this, particularly for chillers or HVAC, I don't like seeing curves like this because that kind of curve, if you try and fit it to, say in Excel, there's no curve that will really fit those shapes. And if you'll notice, we have load on the x-axis, and load is also a factor in the data on the y-axis. It's tons on the x-axis and kW per ton on the y-axis. Don't have tons on both axes. It just makes it a more complicated curve like this. If you just plot the data as kW versus tons, you essentially get a straight line. And so there's the same data shown as just kW versus tons and the same two clouds of data. The point here is the title says a regression model may need bins. You need to categorize the data. You don't want to draw a single line through both clouds of data like that. It might be okay in some cases, depending on what your purpose is, but obviously you get a better model if you segment the model for one chiller versus two chiller operation in this case. An example using schedules. One of the chart types in ECAM is a grouped box plot. So the box plots, it segments the data by percentiles. So you'll have your median and your average at the 25th and 50th percentiles, and then the higher percentiles on both sides of the average. And so if we look at this chart, the black line is the median value. The red line is the average value, and that average value is pulled up because those points at the left and right of the chart there, in this area here, on the left and the right of the chart show a lot of overnight usage on some days. And there's other ways you could look at this data as well. But if you contrast the July profile on the left with the August on the right, you can see that those overnight usage has dropped way off in August relative to July. An interesting thing here is that an easy way to estimate the potential savings there, it's slightly conservative, is just by subtracting the median from the average for those hours when when the lights or whatever it was left on overnight. That's a simple way to estimate the potential savings if you can correct that operation. So again, this is using interval data, hourly data, and we can look at the load shapes, the power versus time of day, and look and see how often things are turned off in a consistent fashion. So all of you are familiar with degree day models, and we have a slope for heating and a slope for cooling and a base temperature. There's analogous things in interval data models where we'll have change point temperatures, the temperature at which the slope changes, just like we changed from cooling degree days to heating degree days at some base temperature. Here we're going to change the slope. So we'll have a temperature, say the typical office building will have a minimum load at some temperatures, typically in the mid 50s. Above that, if we have an economizer, you'll have a fairly steep slope as cooling is required more and more, mechanical cooling. And then once the economizer is no longer operating and the damper is at minimum position, you'll have a slightly lower cooling slope. And if you run out of cooling capacity, the slope will go to near zero over on the far right. Things will try and run harder, but they really can't put out any more cooling. And so it gets near flat. If you have a heat pump building, you'll also, or electrical resistance heat, you'll also see slopes on the left side where heating is required, and you'll have a low, relatively low slope for a portion where a heat pump might be operating, and if the heat pump runs out of capacity or you need to add resistance heat, you'll go to a steeper slope on the left side, as shown in the chart here. So with this in mind, there's different types of models that can be used. These are called change point models when we're modeling with interval meter data. And I'm getting to this not so much from the standpoint of CMVP, but for diagnostics. So in his introduction to this webinar that I saw from John, he had this quote. And I think one of the key charts or data visualizations that I'm going to show is an attempt to answer these types of questions. Because these are the important questions. We should try and make answering these questions fairly easy. I agree with his last parenthetical there. It is never that easy. Well, we try and make it as easy as possible, and I think sometimes it can be pretty easy. Oftentimes it isn't. So now I want to demonstrate the interval data regression using ECAM. And I'm not going to get into the details of the use of ECAM. There's an excellent user guide on the SBW site. It is partly out of date. It was for version 6. Like I said, I did version 7 when I was retired. But I do recommend version 7 very highly. And this demonstration will be using version 7. So I'm going to pull Excel over onto the screen you're all seeing now, hopefully. So there's the easiest way to get an initial set of models in ECAM is to use this template, which has our timestamps, and we don't have to have the data at the same intervals. ECAM will oftentimes have interval data at 15 minutes, and you might have for your KW or whatever your dependent variable is. Those will be at 15-minute intervals, and your weather data may be at hourly intervals. So it allows you to have them at different intervals, but oftentimes they're same, and it's of course faster if ECAM doesn't have to try and match up those timestamps. The data I'm going to show, to stay out of trouble with showing proprietary data from a customer or something. This is the blind data from the efficiency evaluation organization. When I prepared ECAM version 7, I used that data set, which I can't remember, I think it was like 267 buildings or something like that, to run through all those buildings in an automated fashion and create models and see how the performance was, how well the model matched the actual data. And this was, Evo set up these test data sets for people to do that very thing and compare models. And I'm happy to say that version 7 models were as good or better relative to any of the publicly available models that were available when I did that in early 2021. You can do slightly better. I think that there was a proprietary model that used some machine learning that was better than the other models. And one way you can do better is if during the baseline period, if energy use is not consistent with regard to time and temperature, that you can adjust for that trend. That gets into contractual issues about how you treat an inconsistent baseline. And I'm not going to get into that today, but we have ways of looking at that to see whether the energy use is consistent during the baseline period, and I'll show that. So this is the template for doing this, and for this purpose, like I said, it was you can specify what model types you want to use. I'm going to allow ECAM to figure out the model types. ECAM is going to figure out the day types. It's going to figure out the hour types, and that's why I like ECAM version 7, because it does this automatically, but in a transparent fashion. It shows you what they were after the fact and creates these models. So let's see what these are going to look like. So if we have this template set up with this data, I'm going to have it in a folder. And under the M&V utility menu, I've got automated M&V modeling. And then I'm going to pick this building 189 to create a model for. So it'll do a group of buildings from a folder. So if you can do many buildings, I wouldn't recommend doing too many at one time. This is Excel, and you might have some memory creep or things like that, and use up all your resources if you try to do 100 buildings at a time. But doing 20 buildings at a time probably is no issue. I don't remember how many buildings I did at that time when I was running through the 267 Evo buildings. So for doing these models with interval data, it takes anywhere from 90 seconds to 10 minutes, depending upon the complexity of the model that needs to be created. If you have relatively few day types and relatively few hour types, combinations, and the models aren't too complicated, it can be a minute and a half. In this case, I know, because I tested it before we did this, that these models will take about 2.5 minutes to create. We'll have a very robust model. There is a caveat to this fully automated approach, and it's not really a caveat, but what I should say is it's possible to even further improve the models beyond what is done in the fully automated fashion. For purposes of performance and creating these models relatively quick, I limited the models to having a single change point. If you think back to the chart I showed earlier that showed all the potential slopes in an electrically cooled and heated building, there was something, I don't remember, 5 different slopes or something like that that were possible. So I'm limiting this to a single change point, which means 2 slopes. You can further improve the models if it's warranted for the building that you have by going to a more complex model that might have 3 slopes. In most cases, that is sufficient. I'll pull up that article about my home, and there's the rare occasion as we go to more and more fully variable speed systems, it is appropriate to have a polynomial curve fit, something between a second and a third order polynomial, depending on the controls within the building. But usually, and it worked out in my case, having 2 slopes on the cooling side, and actually I think I had 3 slopes, it modeled the building just as accurately as having a full polynomial. I did a test of that, and I think I wrote it up and included it in that article on the Evo website. So the caveat here is that we're limited for the fully automated model to having just 2 slopes. You can go back after the fact and look at those models and see if you think another slope is warranted and change those, input the slopes, the type of model you want into the template and rerun it. So this is done now because it just stopped. So I'm going to go pull up the output. And we'll look at a few different charts here. So here's the summary output. And there should be some things here that are fairly familiar. We have the R-squared for the model and the root mean squared error. I should have got these two, the coefficient of variation of the root mean squared error. So we have a very good model. And here we have the model fit chart. This is kind of a interesting thing to me, is that normally R-squared with a single curve is pretty simple, but here within this model, we have multiple day types and 4 occupancy periods per day. I divide the data for a day into 4 periods, so consider them a startup period, an occupied period, a shutdown period, and the unoccupied period. So 4 different data groupings. I'll talk a bit more about that. But after all is said and done, if you just plot the actual data versus what the model predicted and calculate the R-squared for that, you get the correct R-squared. So you can look at your model fit that way and see how well things fit. One of the other important charts that is one of the things that's not as practical when you only have monthly data, but with any interval data, you just don't have enough data with monthly, but you can look and see if energy use is changing over time. And that's the purpose of this residuals versus time chart. The residuals are the difference between the actual data and what the model predicted for an individual point in time. And so all of the 8,760 hours in the year, or whatever I had in the baseline here, I do have a 8,760, it looks like in this one. Close. I had 8722 data in this baseline model. All of those points are reflected here. So you can look and see if there's a slope to this fit over time and tell you whether the energy use, after accounting for the individual variables, the independent variables, if the energy use was changing over time. So let's look here at the individual models. So here's starting off with the last one that was created. We have day types of Tuesday, Wednesday, Thursday, Friday, Saturday lumped together for the unoccupied period. We can go to the left and see a model for the startup for those days, for the shutdown for those days, etc. And you might see different clouds of data, and that's because we've grouped into 4 time periods during the day. There could be an hour within that one of the four time periods that doesn't really match the other hours, or there could be a gradual increase in energy use during startup, for example. So the energy use each hour is going to be slightly different. That is also accounted for, which is why we see multiple fit lines here. The light blue line here that's being shown, let me zoom in just a little bit on this picture here. So the light or medium blue is the modeled line. Then we adjust the model for the deviation between the different hours within the time period. I can't, in the time we have here, go into huge detail about how ECAM decides what hours of the day to fit into the 4 periods, the occupied, unoccupied, startup, and shutdown. But I got to say, there's a couple things about it. First of all, important to know that the names that are actually shown here, this is the shutdown period, may or may not actually be any sort of shutdown period, and it certainly may not reflect what the building's shutdown time period is. What it is, most of the time for a typical building where you have, say, an office building or a retail store where it's unoccupied overnight, it starts up in the morning, it's occupied during the day, shuts down at night, and then it's unoccupied. Those labels, in this case shutdown, will be reflective of the actual building. But a building that has an unusual schedule, and perhaps they're occupied at night and not during the day, then those labels will not be correct the way we think of them in common English. So I need to be aware of that. I had to apply some label to them, and that's what I did, for better or for worse. The other thing to know is that these segmenting the data into those periods is actually quite robust in ECAM, because it is done in a brute force manner where every grouping for 4 time periods in a day, going from 1 to 19 hours long, is examined and checked for how well it fits the actual data. Every possible combination is examined. So you could have unoccupied for 1 hour in the morning, startup for 1 hour in the morning, occupied for 1 hour, and then unoccupied for 19 hours in the afternoon. It'll check that. Or conversely, it could be 4 6-hour even periods for the 4 time periods. Every one of those is examined, and the ones that give the best fit to the model are the ones that end up being used. So it's a brute force approach, but it's highly robust because of it. So it takes a little time, but it works out pretty well. So it's kind of tedious to try and look at all of these individual ones together here. I will go back and show what some of this data is, and then I'll talk about the value of this data from the diagnostic standpoint. Let's just pick another one here. So if we zoom in a little bit again here. So I'm gonna find a more interesting one here. Okay, so this gives the type of model, 3 parameters. If a model has 2 slopes, it's going to be a 3 parameter or 4 parameter model. In this case, the slope is flat on the left side below the change point, below about 40 degrees. The change point value here is 40 degrees. And we have a slope where cooling is required going off to the right. So it defines the model type. Again, for this individual submodel, we get the R squared and the CVRMSE for the submodel. Lots of other statistics to look at if you like. Now it's tedious to look at all of these individually. So there is an option here to create a matrix so you can look at all of these in one place. And this takes a little bit because, again, there's a lot of data here, and I'm going to create thumbnails of all of these. There's also one here. If you do a baseline and a post model, it'll also create thumbnails of those. It won't show the data. It'll just show the fit lines for each of these submodels with the baseline line fit and the post period line fit on the thumbnails, so that you can see where savings occurred, during what day types and occupancy periods were you getting savings. Wait a moment for this to show up. So there's the picture with all our thumbnails and the labels for each of these occupancy periods. And you can see these here, I'll show you something why this, so my occupancy period here is shown as the low use period. Doesn't make intuitive sense. In this case, the label probably doesn't make sense. Let me zoom in to make sure you guys can see that okay. So here's on the left chart here, it says Monday unoccupied, but it's the lowest use chart here. Well, so let me leave this chart for just a minute. We're going to look at a load shape, a load profile for each day of the week. This is one of the many charts you can get from ECAM, and you don't have to do modeling to do this. You can, it's just a standard time series charts, load profile by day type or load profile by day of week. It's a standard output you can do with your interval data to start with. But you can see these different load shapes, and you can see it's low use during the middle of the day, high use in the afternoons and mornings. Again, I'm blind to this data. This was part of the EVO data set, so I can't make any informed commentary about that. But that's the reason why those labels in this case don't make sense, but the time periods are useful categories. So let's go and see what the ECAM, I'll leave this for a minute. So that's the load profile showing all the different day types. And again, I'll zoom in just a little bit to make sure everybody can see that. So each day of the week is represented as a separate load shape. We have hour of day on the x-axis and whatever the dependent variable is, kW, usually on the y-axis. After we do the day typing, we get a similar load shape. We group the day types that are similar. You can see there's very tightly grouped days here that are pretty close, but then Sunday here, it deviates. It's the same on the left part of the load shape, but on the later hours of the day, it deviates. So probably have a different load shape for Sunday, but a lot of these other weekdays will be lumped together. So this shows the same load shapes, but it broke it into the day types. We've got Sunday, Monday, holiday, and then Tuesday, Wednesday, Thursday, Friday, and Saturday are all lumped together and modeled together. So back to my chart matrix here. So we can see the shape of, and how well the fit is for all of these different models. Now, what does this end up doing for us? One of the great things, I think it's great, and this was the thing I mentioned, a fellow named Doug Finn Bell. It was the Colonel, his idea was the kind of the initial start for this many years ago when I was working for Honeywell, is how can you determine what is unusual behavior? Open up one other chart here, if I've got it handy. So most of you are probably familiar with a typical heat map of energy use, and heat map is color coded. So in this case, let's say low energy use is green and high energy use is red. And in this case, I've got dates. I'm trying to show the colors and nothing. These are dates going down the rows here, and these are hour of day going across the columns. So what does this typical heat map show us? Well, it shows us that energy use, and this is not for the building we're looking at right now, so don't get confused by that. This is for a different building, but this is what we typically see, say for an office building or retail building. Energy use is low at night, shown in green. It's higher during the day, and it's higher during the summer months, and it's shown in red. That doesn't tell us much. We knew that before we ever looked at any data. So what we want to do is look at the data. Is it unusual? So instead of plotting in the form of a heat map the actual data, we look at the deviations from the model in the same type of form. And so there's a output for this that shows color coding, the deviation from what was expected in our color coding. Now, and there's a key to this here. I'll zoom in on this so we can see it a little better. So deviation from expected in this form of standard deviations from what was expected. So it's statistically meaningful. So I've got 3.5 standard deviations, and higher is a dark red if the energy use is high. If it's 3.5 standard deviations or lower, it's a dark green, and then gradients every half a standard deviation in between to color code the deviation in energy use. So let's zoom out and look at the colors here. There's a couple of interesting things here. We'll often see this early morning, late afternoon, and you'll see the colors change at a certain point in time. And if you go back and look at this, in this particular case, what happened here, this is, zoom in so we can see the date. This is November 2nd is when these colors changed. Well, that's the change in daylight savings time. So depending on the direction the colors changed, either the time clock for your data, the timestamp for your data did not change with daylight savings time, or the building isn't tracking its operation with daylight savings time. So that's just an example of the type of inference we can draw from this, that we have a data or a building issue right there. The other things here, again, because I'm blind on this particular building, was part of the EVO data set, I'm not going to try and draw any conclusions here, but you will often go through it look at a building and you go through, and all of a sudden the data changes from largely green to largely red and orange. Say in this part here, maybe it changed to red and orange as we went here. Well, that indicates a change in operation, a change in energy use. Maybe the schedule changed, and so it's just, you know, later hours that all these hours change to red. So if you're following the building over time, and if this type of thing is kept updated on a weekly or monthly basis, you can easily see when things changed and by how much they change, and what the energy impact change is. You can, because these are deviations from what was expected, if the data is in terms of kW, you can actually sum the data points in the time period that changed, and that's the energy impact of that. So to me, this is a very powerful way of looking at the data, identifying when things changed, what day they changed. Now here we haven't filtered for day of the week. We can do that in other ways, but see if it changed at a particular hour of the day or day of the week or season, what have you, and see when things changed, how much they changed, and inform your customer or ask your customer what things changed if there is reason for it. When we're creating a baseline model, of course, this is a problem that I think can become a contractual issue. If you have a baseline where things change suddenly at the latter part of the baseline, you know, it's a challenge with just monthly data. If you're doing a big group of buildings for a performance contract, one building, perhaps it doesn't matter. If you're doing a single large building and things change during the baseline, you need to handle that as an adjustment somehow. The interval data allows you to figure out how to make that adjustment, and then contractually how to handle the fact that your energy use wasn't consistent over the baseline period. So that's what I wanted to show for now. I've got another building we could look at as well, but we've got 15 minutes left, and so I think it's a good time to stop and answer any questions if I can.
All right. Hey, Bill, can you show us how you would be able to find or identify deviations? Like, for example, let's say you're doing a performance contract and you're using 12 utility bills. You know, you're not doing this, but you've got interval data. You might as well look and see, can I find why they're using more energy? How would you go about that? What would you do?
So I would create this chart. I would go through and create a regression model. They're simple approaches. I can go through them, but I'd start this. This is the most thorough, robust approach, is to create a regression model, especially if you have a full year of data, but even if you have less, and look at this and look for either going up, particularly if you're going, up or down the rows, and look for a sudden change in the color of the data. Most of the data, if the model's matching perfectly what the actual data is, the color will be white. If the energy use is low, it's going to be green. If the energy use is high, it's going to be red. So if you see a period where it's going from, a light color, white, red, or green, and suddenly goes to a darker red and it persists, that's a point in time when things change. So if I suddenly here, if all this data suddenly turned redder, that would be indicate an increased energy use going forward. There's other things we can do just looking at the time series of energy use, simpler approaches, but then you've got the issues of trying to correlate it with weather and things. Maybe there was a hot spell or something. This takes all the weather and time and day type and everything into account, looking at it here.
That's good. Okay, that's good. That's really good. All right, good. Okay, so let's go through some of the questions from the other folks. Okay. Oh yeah, someone wanted to know if materials will be shared. Yes. Okay. Yeah, so we got to thank you for not for explaining the reason not to do regressions on kilowatts per ton as a function of time. Thank you for that. someone else. Oh, no. Okay, move on to the next one. Okay, is there any chance this will ever be developed to run on a Mac, or will the executable be always confined to Windows machines?
Yeah, Mark, sorry about that. I'm retired and I don't work on a Mac, so I don't see it happening. I don't know how well Windows emulation works and if that would work on a Mac. I don't, you may have tried that or I don't know.
Yeah, or you just get another machine and have it just for that. That and other things, you know. But, okay, can the residuals versus time chart be used to check for autocorrelation? And before you even answer that, maybe you can explain briefly what autocorrelation is and why anyone cares, or why we should care.
Oh boy, this we're getting into the weeds. I'm an old retired guy.
Well, you can do it simply.
My friend Phil. Boy, Phil, I'll get even with you. So autocorrelation is an indicator that one of the things it is you don't have as much effective data as you think you have. The prior data or the current data points are related to past data points in some fashion, and so you don't really have as much data for the purposes of thinking about uncertainty as you think you have, and that their points are related. Points are related to each other in ways other than you're treating the independent variables. So yeah. There is an output here. Hide the questions pane for a minute. So I have here complete autocorrelation function chart and how many points it goes out to is dependent upon whether you're running hourly or daily models. So I have on this summary of the model, the same place we had the model fit chart, go over to the right, there's now in version 7 an autocorrelation function chart that will tell you what the autocorrelation coefficient is for different lags. And so I would just, if you do this modeling, just look at this chart and see, and here you can see that probably every 7 days or every day. So once a day we have a relatively high, but points are related to the same time period the day before, but beyond that they're not autocorrelated. So hopefully that answers the question.
Yeah, I don't know how it's, well, I'm gonna simplify the autocorrelation or put it in more lay language even, and that is, buildings, if you're looking at interval data, you might be looking at hourly data. And if the hour before is affecting the hour after, then you have autocorrelation, or a couple hours after, or 3 hours after, and I think that's what that's about. And ideally, each hour would be a totally independent entity and have nothing to do with the data, the hour that came before it. Is that right, Bill?
Yeah, I think that's good.
Okay. What's the current version of ECAM, and where can it be obtained if not from SPW? Yeah, can you go online somewhere and show us how to download that?
So the SPW has near to very current version. It's version 7. It's on the SPW website. I can pull that up.
Okay. So I'm still seeing your Excel. Oh, there we go. Okay, good.
So if you do SPW Consulting ECAM in a search bar, and then you'll get to resources. Now I have made a couple changes since this was posted here. Like I said, I don't recall what they were. Probably pretty minor. So you can either get it directly from me, or I'll check with John, since we post the resources for these webinars, and they'll have the PowerPoint and stuff. I don't know if he'd also host or have ECAM for the participants of this webinar or not, but I can have the template that I use for the regression and the tool itself. There is, I will mention, let me click on this. Then they call it version 7 a beta version. I I don't consider it that. It's all I would use. A lot of improved things there and very heavily tested. To user guide. User guide is very complete. It's 160 pages or something like that. They've also got a link I posted on here about what I posted on LinkedIn after it went in. Call it an unsupported beta version. There is really no support for ECAM anyway. I don't know. Somebody from SPW can pipe in if somebody actually there, but I don't believe, as far as I know, I don't believe they have any funding or resources to provide any support. I will answer questions if people have. If I get inundated, I will cease, but I haven't never been inundated with questions. I will answer questions. It may not be real timely. I might be out fishing or whatever, and but I will try and answer the occasional question. The hardest part about ECAM is just getting started. And once you get started, I need to say one other thing, and I'm glad these questions came up, is I'm an engineer, not a programmer. My programming skills, as far as the capabilities of the tool, frankly, awesome. As far as the robustness of it, yeah, so-so. Gina Hicks at SBW did a lot to improve the robustness, because she is, in addition to having 2 degrees of electrical and mechanical engineering, is a much better programmer than me. And so it's a lot more robust than it used to be. But I will say this, if you do things in a manner that I didn't anticipate and didn't get caught, you could have a problem. And so the other thing I always need to say in these webinars, and it's always a shame that I have to say it, but one of the things I do is I put Excel into manual mode for doing some of these processes, because some of these formulas, I try and do more stuff in code than formulas, so formulas don't have to recalculate all the time, because some of the formulas are complicated. And a lot of the things, in fact, if we go back here and look at my output, some things are left as formulas, but generally just in the first row. You see I have formulas here in the first row. Let me zoom in a little bit here. So I have formulas in the first row of the output so that you can duplicate things and copy it down if you want, but all subsequent rows are changed to values so that things don't get recalculated all the time. So anyway, so Excel gets put into manual calculation mode, and if you have a bug or an error, and it could be left in manual mode, and you are wondering what is going on, my Excel is not working, and you're off trying to do something else, not even related to ECAM. Well, it's ECAM's fault, okay? It's my fault. Your Excel got left into manual mode, so you got to be aware of that. Once you're familiar with ECAM and you're doing things in a expected fashion, almost never happens, okay? Almost never. But starting off, sometimes more, just trying to get familiar with the tool, you might be doing something wrong and it's not handled, even though there was a lot of work done to make it better, and it's much better, it still might be left in manual mode. So, gotta say that.
There's bugs everywhere. So this F, what do? Just press F9 to make it calculate? Or what's that? I know there's an F command in Excel to make it calculate.
F9 will do a recalculation, but it won't put it back into automated mode. So you got to go to formulas in Excel, the formulas menu, regular formula, then calculation options.
There you go. Okay.
And make sure it's not stuck in manual.
Perfect. Okay, another question. Can ECAM be used in manufacturing facilities with production counts in addition to weather data, start, stop, times, etc.?
That's a highly qualified yes. You can do it relatively easily if you can bin their production values, and so that they become an additional category instead of a continuous variable. True multiple regression with ECAM, where you have multiple continuous independent variables. I mentioned continuous and categorical variables. You can't do that very easily. You'd have to do some customization.
Okay. Okay.
And I see a note here that SPW does try and provide support and answer ECAM questions, but they won't do it for version 7 apparently. So
Is that in the manual at all? How to do an independent variable like production?
No, you could, okay, well, let me just say one more thing on that. If you don't have more than one continuous independent variable, if there's only one production variable, ECAM can do that absolutely. But if you need to do both, you know, two different production variables or production and ambient temperature and things like that, then you need to probably bin up or categorize at least one of those additional variables. One continuous variable is the rule. It doesn't matter what that continuous variable is.
Okay, do you have, can you make ECAM work in Celsius, or does it always have to work in Fahrenheit? Is there an easy switch to make it work in Celsius?
It doesn't care. It doesn't care what the independent variable was. It doesn't know that it's Fahrenheit or.
Oh, it's just looking at numbers.
And I don't think, yeah, this is where being out of the game for a while, I don't think that there's, I think I label charts as something, but and whether there's labels that are put out automatically that say Fahrenheit, that could be, but all you'd have to do at the worst case is edit text. The ECAM doesn't care what the units are.
Okay, that's interesting. Is ECAM able to generate reports with pre-selected outputs? Do you have these pre-selected reports?
There is an output models and savings report. So you can look and see if that gives you what you want or not. There's no customizable report.
Okay. How do we get the data set that you were demonstrating from EVO? Is that public?
It's public. I'm not sure if you have to be a member of, be a member of EVO or CMVP, but it is, I don't think so. I think you can just get the data and it is public. So.
All right, that's it for my questions. Hey everyone, thanks for coming. Bill, do you have any last words?
No, I just want to thank you everybody for attending, and again, thanks to John and Abraxas, and I hope this was worthwhile for people. Thank you.
This is great, and I'm glad we have it on. Glad we have it recorded. Thank you everyone for showing up. I hope to see you next month and months afterwards.